In this lecture, we'll answer two questions. In the first question, we'll find out the size of this angle APC. This is equals to x. So we have to find out the value of this angle, angle x. And in the second question, we'll find out the length of line 7 CD. This is equals to x. So we have to find out the length of line segment x is equals to CD. So we start with the first question. In the drawing, we have triangle ABC. We know that BP equals to PC. So if we define the length of line segment BP as A, then PC must be also equal to A because they are equal to each other. So BP equals to A, and therefore PC must be also equal to A units in its length. We know that this is angle ABC. This equals to 15 degrees inside. This is angle ACB. This equals to 30 degrees inside. Again, our task is to find out the size of this angle APC. This equals to x. So we have to find out the value of this angle, angle x. So first of all, we extend side CA of this triangle ABC by a straight line. In the next step, we will create angle of 15 degrees at point B in such a way that one leg of the angle will be leg BA or side BA, and the second leg of the angle will create 50 degrees with the first leg BA. So this angle equals to 15 degrees inside according to our construction. In the next step, we will extend this leg until it touches the extended side CA. And we'll define the touching point of the extended side CA with this extended leg. This point is point M. By doing this construction, you can deduce the associated triangle BMC. Triangle BMC is an associated triangle because of the fact that those triangles are both equal to 30 degrees and therefore they are equal to each other. We know that BC is the base of this associated triangle, MBC. So here we can implement rule 20 in this associated triangle, BMC. So I click quickly on rule 20. According to rule 20, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have associated triangle, ABC. Triangle ABC is an associated triangle because AB equals to AC. BC is the base of this associated triangle, ABC. According to this rule 20, the perpendicular AD to the base BC bisect the base BC. That is to say, the perpendicular AD divides the base BC into two halves. the first half is BD and the second half is DC. The first half BD, of course, equals to the second half DC. Each half equals to BC over 2 because BC is being bisected. So BD equals to DC equals to BC over 2. BD equals to BC equals to BC over 2. And this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. Because the fact that AD is perpendicular to the base BC. So we can implement Rule 20 in our triangle, the associated triangle MBC. BC is the base of the associated triangle MBC. According to Rule 20, the perpendicular to the base BC from point M bisect the base BC. That is to say, it divides the base BC into two halves. The first half is BP, the second half is PC. Therefore, the perpendicular from point M must touch the base BC at point P. Why? Because at point P is the midpoint of BC. At point P, the base BC is being bisected into two halves. The first half is BC, that is A, the second half is PC, that is also A. So, therefore, the perpendicular from point M to the base BC must touch the base BC at point P and not in any other point. Okay, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size because it is a perpendicular to the base BC. So by doing all those constructions, we have created the big associated triangle MBC, and here we have. So first of all, we focus on this right triangle MBC, the right triangle MBP. This right triangle MBP. Sinus 30 degrees equals to MB over M. Sinus 30 degrees equals to MP over MB. So write it down. This right triangle BMP sinus 30 degrees equals to MP over MB. And again, in this associated triangle, in this right triangle BMP, sinus 30 degrees equals to MP over MB. The associated triangle BMP, sinus 30 degrees equals to MP over MB. We define the length of the hypotenuse MB as 2B. So, sinus 30 degrees equals to MP over MB. So it is MP over MB. MB is 2B, so we substitute MB by 2B. And finally we get that sinus 30 degrees is 1/2 equals to MP over 2B. So here we multiply this equation by 2B. and we get that MP, the perpendicular MP, equals to 2b over 2. We have 2 in the denominator, 2 in the denominator, so 2 get cancelled. So in total, we found out that MP equals to b units in its length. Or in other words, if MB equals to 2b, then MP equals to b units in its length. It's half of the length of MB. So MP equals to b units in its length. We'll continue to focus on this big associated triangle BMC. In this associated triangle BMC, AB is the angle bisector of angle MBC. Again, AB is the angle bisector of angle MBC. Angle bisector AB divides angle MBC into 2 halves, each half equals to 15 degrees in size. So here we can implement Rule 19 in this associated triangle MBC. So repeat quickly on Rule 19. According to Rule 19, if AD is the angle bisector of triangle ABC, that is to say, angle bisector AD divides angle BAC into 2 halves, each half equals to theta. So AD is the angle bisector of angle BAC in triangle ABC, and therefore angle bisector AD divides the angles, the size of this triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. Repeat again, because of the fact that AD is the angle bisector of this triangle ABC, angle bisector AD divides the sides of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. BD over DC equals to BA over CA. So we can implement Rule 19 in the associated triangle BMC. AB is the angle bisector of angle MBC in the big triangle MBC, and therefore, according to Rule 19, angle bisector AB divides the size of this big triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. So right now, according to Rule 19, the free angle bisector theorem, Rule 19 is also defined as angle bisector theorem. Because of the fact that AB is the angle bisector of angle MBC in triangle MBC, of angle AB is the angle bisector of angle MBC in the big triangle MBC. And therefore, according to Rule 19, this is also defined as angle bisector theorem. Angle bisector AB divides the size of this triangle BMC proportionally. That is to say, MB over BC equals to MA over AC. MB equals to 2B according to our definition, over BC. BC equals to A plus A, that is 2A. So MB over BC is 2B over 2A, and it equals to MA over AC. In this side of the equation we have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. And finally we found out that B over A equals to MA over AC. And again, in total, I found out that B over A equals to MA over AC. So in the next step, we'll focus on this right triangle MPC. In triangle MPC, in the right triangle MPC, we know that B over A equals to MA over AC. Again, we know that B over A equals to MA over AC. B over A equals to MA over AC. Or in other words, line segment AP divides the size of this right triangle MPC proportionally. So line segment AP divides the sides of the right triangle MPC proportionally. And because of the fact that line segment AP divides the size of this right triangle MPC proportionally, line segment AP must be the angle bisector of this triangle MPC. Therefore, according to rule 21, that is the converse rule of rule 19, AP must be the angle bisector of the right triangle MPC. Repeat again that rule 21 is the converse rule of rule 19. So repeat quickly on rule 21. According to rule 21, if we know that line segment AD divides of this the size of this triangle ABC proportionally, that is to say we know that BD over DC equals to AB over AC, then line segment AD must be the angle bisector of this triangle ABC. So if we know that BD over DC equals to BA over CA, that is to say we know that line segment AD divides of the size of this triangle ABC proportionally, then line segment AD must be the angle bisector of this triangle ABC. That is to say, it bisects angle BAC. Divides it into two parts, each part equals to theta. So we already implemented angle bisector theorem, the converse theorem of angle bisector theorem, that is rule 21 in our drawing. Why? Because in our drawing we know that the side of this right triangle MPC has been divided proportionally by line segment AP. So according to rule 21, AP must be the angle bisector of this triangle MPC. That is to say, AP bisects angle MPC into two halves. AP bisects this angle MPC into two halves. AP is angle bisector of triangle MPC. That is to say, angle bisector AP bisect angle MPC. But angle MPC is a right angle. It is equal to 90 degrees in size. So angle bisector AP divides angle MPC into two halves. Each half equals to 45 degrees in size. The first half is this angle AP8 is equal to 45 degrees in size. And the second half of the right angle MPC is this half that equals to x. So the second half is angle x that is equals to 45 degrees in size. So in total we found out that the angle that we are looking for this equation, that is angle APC, is equal to angle x is equal to 45 degrees in size. And again, the answer to the question is the size of this angle APC is equal to x is 45 degrees. So we finish with the first question. In the next step, I present you the second question and we solve the second question of this lecture. In the second question, our task is to find out the length of this line segment CD is equals to x. So we have to find out the value of line segment x is equals to CD. So in the drawing we have a semicircle. Those two angles are both right angles. We know that CQ equals to QP equals to QE. So if we define the length of CQ as A, then QP must be also equal to A and QE must be also equal to A because of the fact that those three line segments are equal to each other in their lengths. In addition, we know that this is point O, that is the center of the semicircle. We also know that this is line segment OE. This equals to 5 units in its length. This is line segment AB. This equals to 4 units in its length. Again, our task is to find out the length of this line segment CD. This is equals to x. So of this is to find out the left of right side x is equal to CD. So first of all, we will join point C and P together by straight line. By joining point C and P, we created the right triangle, triangle CPQ. We have the rule that says that in front of equal sides in a triangle, there are equal angles. So in front of those two equal sides, we know that those two sides are both equal to A, and therefore they are equal to each other. So in front of those two equal sides, we have those two angles that must be also equal to each other, and their sides according to the rule that I mentioned. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. We know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in this right triangle CQP is equal to 180 degrees. Which angles we have in the right triangle CQP? We have alpha plus alpha is 2 alpha plus 90 degrees. In total must be equal to 180 degrees. So write it down. We should know that right triangle CQP, the sum of the angles must be equal to 180 degrees. That is to say, 2 alpha plus 9 degrees, in total it must be equal to 180 degrees. And again, in the right triangle CQP, the sum of the angles must be equal to 180 degrees. That is to say, 2 alpha plus 9 degrees, in total it must be equal to 180 degrees. Here we subtract 90 degrees from this equation, and we'll get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we will divide this equation by 2, and finally get that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. So those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in size. Actually, the right triangle CQP is also an associated triangle. So in any associated triangle that is also a right triangle, we have 3 angles. One of the angles is a right angle, and the other 2 angles, each of them is equal to 45 degrees in size. In the next step, we join points P and E together by straight line. It is given us the question that CE is the straight line. Again, CE is the straight line according to what is given us the question. According to rule 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line CE at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line CQ at point, at the upper side of the straight line CE at point Q? We have this angle, this is the right angle, plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in size. And therefore, triangle PQE is a right angle. Triangle PQE is a right angle, but it is also an associated triangle because of the fact that those two sides are equal to each other. Each of them is equal to A, and therefore they are equal to each other. And because of the fact that the right triangle PQE is also an associated triangle, those two angles, each of them is equal to 45 degrees in size. It is true in any associated triangle, there is also a right triangle. In the next step, we will do a construction, that is to say, we will complete this semicircle to a circle. So we completed the semicircle to a circle. In the next step, we will extend the straight line CE by straight line until it touches the circle. And we'll define the touching point of the extended line CE with this circle. This point is point M. Likewise, we'll extend the straight line PE by straight line until it touches the circle. And we'll define the touching point of the extended line PE with this circle. This point is point N. In the next step, we will join points M and N together by straight line. Likewise, we will join points B, C and N together by straight line, those 2 points. This is perifocal CPN. Repeat again. This is perifocal CPN. Perifocal CPN equals to 45 degrees plus 45 degrees. It is 90 degrees, so it is a right angle. Perifocal CPN subtend on this chord CN. And it is a right angle. So here we can implement rule 5 in our drawing. Repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. This is peripheral angle MAN that is equal to 90 degrees in size, and therefore peripheral angle MAN must subtend on the diameter of the circle. Peripheral angle MAN subtend on chord MN, therefore chord MN must be the diameter of this circle according to this rule, rule 5. So we can actually implement rule 5 in our drawing. One, because in our drawing we have perifocal CPN, that is a right angle. Therefore, according to rule 5, perifocal CPN must subtend on the diameter of the circle. Perifocal CPN subtend on chord CN, and therefore chord CN must be the diameter of this circle according to rule 5. Chord CN is the diameter of this circle according to rule 5. Here we can implement the converse rule of rule 5, this perifocal CMN. So I pick quickly on rule 7. And again, rule 7 is the converse rule of rule 5. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in size. In the drawing, we have a circle. This is perifocal ACB that subtend on chord AB, that is the diameter of the circle. Therefore, according to this rule, rule 7, perifocal angle ACB must be equal to 90 degrees in size. So according to this rule, rule 7, any perifocal angle that subtend on the diameter of the circle must be equal to 90 degrees in size. So we can implement rule 7 in our drawing. In our drawing, in this is perifocal angle CMN, perifocal CMN. This is perifocal CMN that subtend on chord CN. Chord CN is the diameter of this circle, and because of the fact that 5 against Siemens subset on the diameter of the circle, it must be equal to 90 degrees inside according to rule 7. Those two angles are defined as vertex angles. Okay, again, this is angle PEQ, is equals to 45 degrees inside, and this is angle MEN, this is the missing angle. So those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 45 degrees, and therefore this missing angle must also equal to 45 degrees in size. So in this small right triangle E and M, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in size. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we find out the radius of this circle. What is the radius of this circle? We know that the radius of any circle starts from the center of this circle, from the center of the circle, that is actually in this case is point O, and ends on the circle itself. And ends on the point that is located on the circle itself. Therefore, OB is the radius of this circle, because it starts from the center of the circle, that is to say point O, and ends on the point that is on the circle itself. Point B is located on the circle. OB is the radius of this circle. OB in total equals to OE, that is 5, plus EB, that is 4. So in total the radius of OB equals to 5 plus 4, that is 9. So writing down the radius of this circle is equal to 9 units in its length. OC is also the radius of this circle, that is equals to 9. Likewise, ON is also the radius of this circle, that is equals to 9. In the next step, we find out the area of this green triangle, triangle COE. Repeat again, we'll find out the area of this green triangle, triangle COE. What is the area of this green triangle, triangle COE? We know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this green triangle COE equals to the base of the triangle times the height to the base over 2. We'll choose the base of this green right triangle COE as CO. CO is the radius of this circle, is equal to 9 units in its length. So the base of the green triangle COE is CO, according to choose. So it is CO times the height. What is the height of this green triangle COE? The height is also the height, it is the height to the base. It must create 90 degrees with the base. But the height to the base also must create 90 degrees with the extended base. CO is the base, the extended base is CN. The extended base, no, the extended base is CN. CO is the base, and therefore the extended base is Cn. Therefore, we draw perpendicular from point E to the extended base Cn. So actually, this angle equals to 9 degrees in its size, and this angle also equals to 9 degrees in its size according to our construction. We define the touching point of the perpendicular from point E, and this and Cn. This point is point G. CG is the height to the base Cn. CG is the height to the base CO, or CG is the height to the extended base CO, that is Cn. Therefore, we define CG as h. This is the permission for height. So in total, we found out that the area of this great triangle CO equals to the base CO times the height to the extended base, that is h, for this great 90 degrees with the extended base Cn. The base is CO, the height is h over 2. CO is the radius of this circle, that is equals to 9. So substitute CO by 9 times h over 2. So in total, we actually found out that the area of the green triangle COE is equal to 9h over 2 square units in its size. The area of this green triangle COE equals to 9h over 2 square units in its size. Likewise, we'll find out the area of this triangle, the lower triangle, triangle EON. This is the lower triangle, triangle EON. What is the area of this lower triangle, triangle EON? The area of the lower triangle EON is equal to the base of the triangle times the height to the base over 2. That is the area of any triangle, that is the area of this triangle, triangle EON. We choose the base of this triangle EON as ON. And the height to the base ON is h, because of the fact that h creates an address with the base ON. So the height is h. H over 2. So in total, we found out that the area of the lower triangle EON equals to ON times h over 2. ON is the radius of this circle, that is equals to 9. So substitute ON by 9, h over 2. So in total, we found out that the area of the lower triangle EON is equal to 9h over 2 square units in its size. But the area of the green triangle COE is also equals to 9h over 2 square units in its size. That is to say, the area of those two triangles are equal to each other. So we found out that the area of the green triangle COE is equal to the area of the lower triangle, triangle EON. In the next step, we'll find out the area of this big triangle, triangle CON. We find out the area of this big triangle, triangle CEN. What is the area of the big triangle CEN? The area of the big triangle CN must be equal to the areas of the components that it consists of. The big triangle CN consists of those two components. The first component is the green triangle COE, and the second component is the lower triangle OEN. So the area of the green triangle CN must be equal to the area of the green triangle COE plus the area of this lower triangle OEN. Repeat again, the area of this big triangle CN of the big triangle CN must be equal to the sum of the areas of the two components that it consists of. The first component is the green triangle CO, therefore it is the area of the green triangle COE, plus the area of the second component, this is actually triangle OEN. So it is plus the area of triangle OEN. But we already found out that the area of triangle COE equals to the area of triangle EON. The area of triangle COE equals to the area of triangle OEN. Therefore, we can substitute the area of triangle OEN by the area of triangle COE because of the fact that they are equal to each other. So in total, we get that the area of the big triangle CN equals to the area of the green triangle COE plus the area of the lower triangle OEN. But because of the fact that the area of the lower triangle OEN equals to the area of the green triangle COE, we substitute the area of triangle OEN by the area of triangle COE because they are equal to each other. So in total, we found out that the area of the big triangle CEN equals to the area of triangle COE plus the area of triangle COE. That is to say, it is 2 times the area of the green triangle COE. Or in other words, the area of the green triangle CN is twice as large as the area of the green triangle COE. Here we divide this equation by 2, and finally we get that the area of the green triangle COE equal to the area of the big triangle CEN over 2. That is to say, the area of the green triangle COE is half of the area of the big triangle CEN. In the next step, we calculate the area of this big triangle CEN according to the rule that the area of any triangle equals to the base of the triangle times the height over 2. So the area of the big triangle CEN equal to the base of the triangle times the height to the base over 2. The area of this big triangle CEN equals to the base of the triangle times the height over 2. We'll choose the base of this triangle CEN as CE. The base is CE according to our choice. C is the best according to our choice. Times the height. The height to the base must create 90 degrees if the base, or the height to the base must create 90 degrees with the extended base. The extended base CE is CM. CM is the extended base CE. So the height to the base CE must create 90 degrees with the extended base CM. It's very easy to see that NM creates 90 degrees with the extended base CM, because this is the right angle. So Mn is the height to the base, the extended base Cm. Mn is the height. Divided by 2. So in total, we found out that the area of the big triangle Cn equals to the base Ce times the height Mn over 2. Ce, the base Ce in total equals to A plus A, that is 2A. It is CQ, that is A, plus QE, that is also A. So the base Ce equals to 2A times the height Mn. So here, what is the height Mn? In this small triangle EMN, in front of those two equal angles, we have those two sides that must be also equal to each other. They are right according to the rule that said that in front of equal angles in a triangle there are equal sides. So in front of those two equal angles, we have those two sides that must be also equal to each other, and they are right. So if we define the side, the left of side Mn as B, then the left of side EM must be equal to B because they are equal to each other. So therefore the height Mn is B. Mn is B over 2. So today we found out that the area of the big triangle Cn equals to 2AB over 2. Here we have 2 in the denominator, 2 in the denominator, so 2 get cancelled, and we're left only with AB. So in total we found out that the area of the big triangle Cn is equal to AB square units in size. Again, the area of the big triangle Cn is equal to A times B square units in size. The area of this big triangle Cen is equal to A times B square units in size. So in the next step, we'll implement rule 65 in our drawing. We click quickly on rule 65. According to rule 65 is to in any circle, so this circle could be any circle. In any circle, if chord AB intersects with chord CD at point O, then the following equation is to AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. But again, in the drawing of a circle, this is called AB, that intersects with chord CD at point O. The intersection point between those two chords occurs at point O. So in this drawing, the following equation is to AO times OB equals to CO times OD. So we can implement rule 65 in our drawing. Why? Because in our drawing, this is chord AB, intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. So all the requirements of rule 65 are satisfied. Therefore, we can implement here rule 65 in our drawing. So write it down. In our drawing, we have chord AB intersects with chord CM at point E. The intersection point between those two chords A, B, and CM occurs at this point at point E. So all the requirements of rule 65 are satisfied. Therefore, we can implement in our drawing rule 65. According to rule 65, the following equation is true. AE times EB, AE times EB equals to CE times EM. And again, according to Rule 65, the following equation is true. AE times EB equals to CE times CM. AE equals to AO plus OE. Again, A equals to AO plus OE. AO is the radius of this circle, is equals to 9. And again, AO is the radius of the circle, is equals to 9. Plus OE. OE equals to 5 units in itself, according to what is given in the question. Here, OE equals to 5. OE equals to 5. So in total, AO equals to 9 plus 5, that is 14. AE equals to 9 plus 5, that is 14. Times EB. EB equals to 4 units in itself, according to what is given in the question. EB equals to 4. And it is equals to CE. CE equals to A plus A, that is to A. Again, C equals to CQ, that is A, plus QE, that is also A. So in total, C equals to 2A. Times EM. EM equals to 4 units in its turn. EM equals to B. EM equals to B here. The red letter is here is B. EM equals to B units in its turn according to our definition. So in total, we found out that 14 times 4 equals to 2AB. 14 times 4 is 56. So 56 equals to 2AB. Here we divide this equation by 2. And finally get that AB equals to 56 over 2 is 28. And again, we found out that A times B equals to 28. Now we found out that the area of the big triangle CN equals to AB. The area of the big triangle CEN equals to A times B squared in its size. But we just found out that AB equals to 28, so we can write here that AB equals to 28, and from this equation, the area of triangle CN equals to AB equals to 28, we will derive that the area of triangle CN equals to 28 squared in its size. The area of the big triangle CEN equals to 28 squared in its size. So we found out that the area of the grand triangle CO equals to the area of triangle CN over 2. 29. So we found out that the area of the grand triangle COE, the grand small triangle COE, the area of this grand triangle COE is equal to the area of the big triangle CEN over 2. We just found out that the area of the big triangle CN is 28. So we substitute the area of triangle CN by 28 over 2. 28 over 2 is 14. So in total we found out that the area of the great small triangle COE is equal to 14 squared in size. And again we found out in total that the area of this grand triangle COE equals to 14 squared in size. In the next step, we calculate the area of this grand triangle COE according to the formula that says that the area of any triangle equals to the base of the triangle times the height to the base over 2. Repeat again. The area of green triangle COE must be equal to the base of the triangle times the height to the base over 2. This is the area of any triangle, and therefore this is also the area of this green triangle COE. And again, the area of the green triangle COE equals to the base of the triangle times the height to the base over 2. We'll choose the base of this triangle COE as OE. OE is the base. Only our choice. Times the height to the base. The height to the base must rest 90 degrees with the base, so the height to the base must rest 90 degrees with the extended base. The extended base EO is EA. Again, the extended base EO is EA. So the height to the base must rest 90 degrees with the extended base EA. CD creates 90 degrees with the extended base EA. Therefore, CD is the height to the base EA. The height to the extended base EA. So CD is the height over 2. So in total, we found out that the area of the green triangle COE equals to the base OE times the height CO over 2. The base OE equals to 5 units in its length, according to what is given as the question. OE equals to 5. So we substitute OE by 5 times CD. CD equals to X, according to what is given as the question. That is the line segment that we are looking for. So we substitute CD by X. CD is X over 2. So in total, we found out that the area of the green triangle COE is equal to 5x over 2 square units in its size. But we already found out that the area of the COE equals to 14. So can I tell that the area of the COE, the area of the green triangle COE equals to 14. And from this equation, 14 equals to the area of the green triangle COE equals to 5x over 2. We will derive that 14 equals to 5x over 2. Those two sides of the equation are equal to each other. So 14 equals to 5x over 2. Here we multiply this equation by 2 and finally get that 14 times 2 is 28 equals to 5x. Here we divide this equation by 5 and finally get that x equals to 28 over 5 units in its length. 28 over 5 is 5.6 units. So in total, we found out that DC is equals to x, DC is equals to x, is equal to either 28 or 5 units in its length, in terms of numbers. CD is equal to x is equal to 5.6 units in its length. That is the answer to the second question. So in the next step, our sum of the lecture, that is to say, we repeat on the solution of the first question and then we repeat on the solution of this second question. Our task in the first question was to find out the size of this angle APC is equal to x. So we have to find out the size of this angle x is equal to angle APC. So in the drawing we have triangle ABC. We know that BP equals to PC. So if we define the length of BP as A, then PC must be also equal to A because they are equal to each other according to what is given as the question. In addition, we know that this is angle ABC. This is equal to 15 units in its size. This is angle ACB that is equals to 30 degrees inside. Again, our task is first to find out the size of this angle APC that is equals to x. We have to find out the value of this angle x. So first of all, as I already mentioned, BP equals to PC. Therefore, if BP is A, then PC must also equal to A because they are equal to each other according to what is given in the question. In the next step, we extended side CA of this angle ABC by a straight line, and then we created angle of 15 degrees at this point B in such a way that BA is one leg of the angle, and this side creates 15 degrees with the leg BA. Again, the other side of this angle creates 50 degrees with side B of the leg BA. So this angle equals to 15 degrees according to our construction. In the next step, we extended this leg of this angle by a straight line until it touches the extended side CA. We find the touching point of the extended side CA with the extended leg. This point is point M. By doing this construction, we created the associated triangle ABC. Triangle ABC is an associated triangle because of the fact that those two angles are equal to each other. Each of them is equal to 30 degrees in its size. The base of the associated triangle ABC is BC. So here we can implement rule 20 in the associated triangle ABC. Which we can rule 20. According to rule 20, the perpendicular to the base of an associated triangle bisect the base. In the drawing we have the associated triangle ABC. Triangle ABC is an associated triangle because of the fact that those two sides are equal to each other. The base of this associated triangle ABC is BC. According to this rule 20, the perpendicular AD to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. Each half equals to each other. The first half is BD, is equals to the second half DC. Each half equals to BC over 2 because of the fact that BC has been bisected. So the first half is BD, and is equal to the second half DC, and it equals to BC over 2. So we can implement rule 20 in the associated triangle ABC. According to rule 20, the perpendicular from point M to the base BC bisects the base BC. Because of the fact that the base BC has been bisected by the perpendicular from point M must touch the base BC at point P and not in any other point. Why? Because of the fact that point P is the midpoint of BC. Why point P is the midpoint of BC? Because of the fact that at point P, BC has been bisected. The first half of BC is BP, it equals to A, and the second half of BC, the base BC is PC. Each half equals to A. So the perpendicular from point M to the base BC must touch the base BC at point P, not in any other point. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction, because of the fact that MP is defined as the perpendicular. Therefore, each of those two angles equals to 90 degrees in its size. This is the right triangle BMP. In the right triangle BMP, sin 30 degrees equals to MP over MB. And again, in the right triangle BMP, sin 30 degrees equals to MP over MB. We define the hypotenuse MB as 2B. So sin 30 degrees equals to MP over MB. MB is 2B according to our definition. So in total, we should find out that sin 30 degrees equals to MP over 2B. Sin 30 degrees is 1/2. So in total, we should find out that 1/2 equals to MP over 2B. We multiply this equation by 2 and finally found out that by 2B, and finally found out that 2B over 2 equals to MP. We have 2 in the numerator, 2 in the denominator, so 2 gets cancelled, and finally found out that MP equals to units in itself. That is to say, we found out that if MB equals to 2B, then MP must be equal to B. That is to say, MB is twice as long as MP, or MP is half of the length of MB. So in the drawing we have the big triangle M, the big associated triangle MBC. This is angle bisector AB that bisects angle MBC. That is to say, divides angle MBC into two halves. Each half equals to 15 degrees in size. And therefore we can implement here rule 19 that is actually defined as angle bisector theorem. So I put quickly on angle bisector theorem or rule 19. According to rule 19, if AED is angle bisector of angle BAC in the triangle ABC, that is to say, it divides angle BAC into two halves. Each half equals to theta. So we know that AED is the angle bisector of triangle BAC, and therefore angle bisector AD divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to AB over AC. Because of the fact that AD is the angle bisector of this triangle BAC, angle bisector AD divides the size of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. BD over DC equals to BA over CA. So you can implement rule 19 in our drawing. When put in our drawing, this is the associated triangle BMC. AB divides angle MBC into two halves, each half equals to 15 degrees in size. And therefore, the angle bisector AB divides the size of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. And again, because of the fact that AB is the angle bisector of this triangle MBC, angle bisector AB divides the size of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. And again, according to rule 19, according to rule 19, we know that, according to rule 19, we know that that is angle bisector theorem. In the big triangle MBC, in this big triangle MBC, AB is the angle bisector of triangle MBC, and therefore, again, AB is the angle bisector of angle MBC in triangle MBC. Therefore, angle bisector AB divides the sides of the associated triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. And again, MB over BC equals to MA over AC. MB is 2B, BC is A plus A, that is 2A, equals to MA over AC. And again, MB is 2B over BC is 2A, equals to MA over AC. We have 2 in the numerator, 2 in the denominator, so 2 we can cancel. That's why we found out that B over A equals to MA over AC. So in total we should find out that B over A equals to MA over AC. So in the next step, we'll focus on this right triangle MPC. The right triangle MPC, MB, MP, that is B, over PC, that is A, equals to MA over AC. That is to say, in the right triangle MPC, angle bisector AP divides the size of this triangle MPC, the right triangle MPC proportionally. Why? Because B over A equals to MA over AC. And again, in the right triangle MPC, because of the fact that AP divides the size of this triangle proportionally, it means that AP must be the angle bisector of triangle MPC. according to Rule 21, AB is the angle bisector of triangle MPC. Please click on Rule 21. According to Rule 21, if we know that 97 AD divides this size, the size of this triangle ABC proportionally, that is to say we know that BD or DC equals to AB over AC, then 97 AD must be the angle bisector of this triangle ABC. Okay, so 97 AB is the angle bisector of triangle BAC. So DA is the angle bisector of angle BAC in triangle ABC. That is to say, angle bisector DA divides angle BAC into two halves, each half equals to theta. So we can actually implement Rule 21 in our drawing. In our drawing, 97 AP divides the size of this right triangle MPC proportionally. That is to say, B over A equals to MA over AC. And therefore, according to Rule 21, 97 AP must be the angle bisector of triangle MPC. According to Rule 21, 97 AP is the angle bisector of triangle MPC. That is to say, AP divides angle MPC into two halves. Because of the fact that AP is the angle bisector of angle MPC, AP, angle bisector AP, divides angle MPC into two halves. Each half equals to the size of the big angle MPC over 2. The size of the big angle MPC is 90 degrees. 90 degrees over 2 is 45 degrees. So the first half is 45 degrees. The second half is also 45 degrees. So the second half is x. So x equals to 45 degrees inside. So in total we found out that angle APC is equals to x is equals to 45 degrees inside. Here again, angle bisector AP divides angle MPC into two halves. Angle MPC in total is 90 degrees. So each half must be equal to 45 degrees inside. That is to say, the second half of the big angle MPC is equal to 45 degrees inside. Angle APC is equal to x equals to 45 degrees inside. So we finish to repeat on the first question. On the next step, repeat on the solution of the second question. The second question, our task is to find out the length of this line 7 CD is equal to x. So we have to find out the length of line 7x is equal to CD. So in the drawing we have a semicircle. Those triangles are both right angles. We know that CQ equals to QP equals to QE. So we define one line 7 SA. If CQ equals to A, then PQ and QE must be also equal to A because they are equal to each other. So CQ equals to QE equals to QP equals to A. In addition, we know that this is point O, that is the center of this semicircle. Line segment O equals to 5 units in itself. Line segment EB equals to 4 units in itself. This letter is letter B. Line segment EB equals to 4 units in itself. Again, our test, was to find out the length of line segment CD is equal to x, so our text was to find out the length of line segment x is equal to CD. So first of all, so I mentioned before, CQ equals to QP equals to QE, so if you find the length of CQSA, then QE and QP must be also equal to A because they are equal to each other according to what is given as the equation. CQ equals to PQ equals to QC. In the next step, we join point C and C and P together by straight line. By joining point C and P, we get the right triangle CPQ. We have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we know that CQ equals to QP equals to A. In front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if you find the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. You know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles of this right triangle CPQ equals to 180 degrees. So which angles we have inside the triangle CPQ? We have alpha plus alpha is 2 alpha plus 9 degrees. In total, it must be equal to 180 degrees according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle CPQ, the sum of the angles must be equal to 180 degrees. That is to say 2 alpha plus 9 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation. If I found out that 2 alpha equals to 180 degrees minus 20 degrees is 90 degrees. Here we divide this equation by 2. If I found out that the missing angle alpha equals to 90 degrees over 2 is 45 degrees. Those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in size. So actually, this is the right triangle CQP. The right triangle CQP is also an associated triangle because of the fact that CQ equals to QP. So we can write down in general that in any right triangle, this is also an associated triangle. We have three angles. The first angle is the right angle, and the other two angles, each of them is equal to 45 degrees. This is true in any associated triangle, that is also a right angle. So in the next step, it is given us the equation that CE is a straight line. So if you focus on the upper side of the straight line CE at point Q, if the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line CE at point Q? We have this angle that is the right angle, plus this missing angle, so that the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the next step, we join points P and D together by straight line. By joining points P and D, we get the right triangle PQE. The right triangle PQE is also an associated triangle because of the fact that those two sides are equal to each other. Each of them is equal to A, and therefore they are equal to each other. Therefore, the right triangle PQE is also an associated triangle, and the three angles in any right triangle that is also an associated triangle are as follows. The first angle is 90 degrees, and therefore those two other angles must be equal to 45 degrees in the sizes each of them. So those two angles are equal to 45 degrees. In the next step, we completed this semicircle to a circle. So this is the circle that we created here. And then we extended side CE by straight line until it touches the circle. We define the touching point of the extended side CE with this circle. This point is point M. Likewise, we extended side PE by straight line until it touches the circle. We define the touching point of the extended side PE with this circle. This point is point M. In the next step, we join points M and N together by side. We join points M and N together by straight line. We join points C and N together by straight line. This is angle CPN. Angle CPN equals to 45 degrees plus 45 degrees is 90 degrees. So angle CPN is the right angle. Angle CPN, peripheral angle CPN, subtend on chord CN. Peripheral angle CPN that is the right angle, subtend on chord CN. So you can implement rule 5 in our drawing. A bit quickly on rule 5. According to rule 5, any perpendicular is equal to 90 degrees inside must subtend on the diameter of the circle. In the drawing we have a circle. This is perpendicular MAN. We know that perpendicular MAN equals to 90 degrees inside. Therefore, according to this rule 5, perpendicular MAN must be perpendicular MAN must subtend on the diameter of the circle. Perpendicular MAN subtend on MN. Therefore, MN must be the diameter of the circle according to this rule 5. So according to rule 5, any perpendicular is equal to 90 degrees inside must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. In our drawing we have perpendicular CPN is equal to 90 degrees inside. Therefore, perpendicular CPN must subtend on the diameter of the circle. Perpendicular CPN subtend on chord CN, and therefore chord CN must be the diameter of the circle according to rule 5. Chord CN is the diameter of the circle. This is perpendicular CMN. Perpendicular CMN subtend on the diameter of the circle, that is CN. Therefore, perpendicular CMN must be equal to 90 degrees inside according to rule 7. So, rule 7 is the converse rule of rule 5. Let's click on rule 7. According to rule 7, if a perpendicular subtend on the diameter of the circle, then it's equal to 90 degrees inside. In the drawing, we have a circle. We know that this is perpendicular angle ACB that subtend on the diameter of the circle, that is AB. Therefore, according to this rule 7, perpendicular ACB must be equal to 90 degrees inside. So according to this rule 7, any perpendicular that subtend on the diameter of the circle must be equal to 90 degrees inside. So we can implement rule 7 in our drawing. Why? If we focus on this perpendicular CMN, perpendicular CMN subtend on CN, that is the diameter of this circle. Therefore, according to rule 7, perpendicular CMN must be equal to 90 degrees inside. So this angle is the right angle. Those two angles are defined as vertex angles, so we know the vertex angles are equal to each other. But this angle equals to 45 degrees, and therefore this angle must be also equal to 45 degrees inside according to the rule that I mentioned. So this front angle CEMN, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 45 degrees inside according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we calculated the area of this green triangle COE. What is the area of this green triangle COE? But before that, we found out the radius of this circle. The radius of this circle equals to OB. Why? Because the radius of any circle starts from the center of the circle, that is to say point O, and that's on the point that is on the circle itself. So OB is the radius of this circle. OB in total equals to OE, that is 5, plus EB, that is 4. So in total, OB equals to 5 plus 4, that is 9. So the radius of this circle equals to 9 units in itself. OC is the radius of this circle, that is equal to 9. ON is also the radius of this circle, that is equal to 9. Likewise, AO is also the radius of this circle, that is equal to 9. So in the next step, we calculated the area of this green triangle, triangle COE. We know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of the green triangle COE must be equal to the base of the triangle times the height over 2. The height to the base over 2. We choose the base of this triangle, the green triangle COE, as CO, and CO equals to 9. The height to the base must create 90 degrees with the extended base. The extended base CO is CN. MN, actually, we extended the base CO, and this way we got CN. Then from point E, we do perpendicular on the base CN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We find the length of line segment EG as H. H is the height to the base CN. And again, H is the height to the base CN. CN is the extended base CO. Therefore, the height to the base CO is h, because it's greater than 90 degrees with the extended base CN. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to construction. So in total, the area of this rectangle CON equals to the base CO times the height h over 2. In the end, in total, we should find out that the area of the rectangle COE equals to the base CO times the height h over 2. So in total, the area of the rectangle COE equals to 9h over 2 square units in size. Repeat again, the area of the rectangle COE equals to 9h over 2 square units in size. Likewise, we calculated the area of this lower triangle OEN. The area of the lower triangle OEN equals to the base of the triangle times the height over 2. The area of the lower triangle OEN equals to the base of the triangle times the height of the base over 2. We choose the base of this triangle OEN as ON, and ON is the result of the circle, this is 9, times the height. The height is h because it's greater than 90 degrees with the base ON. So in total, the area of this triangle OEN equals to the base ON times the height h over 2. So in total, we should find out that the area of the lower triangle EON equals to the base ON times the height h over 2. ON is the radius of this circle, that is equal to 9. So we substitute ON by 9. In total, we should find out that the area of the lower triangle EON equals to 9h over 2. But the area of the rectangle COE also equals to 9h over 2. Therefore, we found out actually that the area of the rectangle COE equals to the area of the lower triangle EON. In the next step, we calculated the area of this big triangle CEN. Actually, the big triangle CEN consists of those two triangles. It consists of the rectangle COE and it consists of this triangle OEN. Therefore, the area of the big triangle CN must be equal to the area of the two components that it consists of. The first component is the rectangle COE. Therefore, this is the area of the rectangle COE plus the second component that it consists of, this, the lower triangle ON. Therefore, it is plus the area of the lower triangle ON. So in total, we found out that the area of this big triangle CEN equals to the area of the great triangle COE plus the area of the lower triangle OEN. But we already found out that the area of the great triangle COE equals to the area of the lower triangle ON. The area of the great triangle COE equals to the area of the lower triangle OEN. So the area of the big triangle CN equals to the area of the great triangle COE plus the area of triangle OEN. But because of the fact that the area of triangle EON equals to the area of triangle COE, we can substitute the area of triangle OEN by the area of triangle COE because they are equal to each other and their sizes. So in total, we should find out that the area of the big triangle CN equals to the area of the great triangle COE plus the area of the great triangle COE. That is to say, the area of the big triangle CN equals to 2 times the area of the great triangle COE. Here we divided this equation by 2 and finally found out that the area of the great triangle COE equals to the area of the big triangle CEN over 2. The area of this great triangle COE is half of the area of the big triangle CEN. In the next step, we calculated the area of this big triangle CN according to the rule that the area of any triangle equals to the base of the triangle times the height to the base over 2. And again, the area of the big triangle CN equals to the base of the triangle times the height to the base over 2. We choose the base of this big triangle CN as CE, and the height to the base CE must create 90 degrees with the extended base CE. The extended base CE is CM, and NM creates 90 degrees with the extended base that is CM. Therefore, MN is the height to the extended base CM. So in total, we found out that the base of this big triangle CEN is CE, and the height to the base is MN divided by 2. So in total, we found out that the area of the big triangle CN equals to the base CE times the height to the base MN. MN is the height to the base because of the fact that it characterized with the extended base CE. MN characterized with the extended base CE, that is CM. This is the right angle. So in total we should find out that the area of the big triangle CN equals to CE times MN over 2. CE is A plus A, that is 2A. C equals to CQ, that is A, plus QE, that is also A. So CE in total is 2A times MN. MN is B. So in total we should find out that the area of the big triangle CN equals to 2A times B over 2. We have 2 in the numerator, 2 in the denominator, so 2 get cancelled, and total this expression equals to A times B. So in total we should find out that the area of the big triangle CN equals to AB square root in size. The area of this big triangle CN equals to A times B square root in size. But again, the area of the big triangle CN equals to A times B square root in size. In the next step, we implemented rule 65 in our drawing. I put clicking on rule 65. Rule 65 is true in any circle, so in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Here we can implement rule 65 in our drawing. Why? Because in our drawing, this is chord AB. That intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. So all the requirements of rule 65 are satisfied, and therefore we can implement rule 65 in our drawing. So again, in our drawing, we have chord AB that intersects with chord CM at point E. Point E is the intersection point of chord AB with chord CM. So all the requirements of rule 65 are satisfied, and therefore we can implement here rule 65. According to rule 65, the following equation is true. AE times EB equals to CE times CM. And again, according to rule 65, the following equation is true. AE times EB equals to CE times EM. AE equals to AO, that is 9, plus OE, that is 5. 9 plus 5 is 14. So A in total equals to 14 times EB. EB equals to 4 units in itself according to what is given as a question. So EB is 4. So in total in this side of the equation we have 14 times 4 equals to CE times EM. CE equals to CQ, that is A, plus QE, that is also A. So CE in total equals to 2A. And again, CE equals to 2A times EM. EM equals to B units in itself according to our definition. So EM is B. So in total we should find out that 14 times 4 equals to 2A times B. 14 times 4 is 56. 56 equals to 2AB. If we divide this equation by 2, and finally found out that A times B equals to 56 over 2 is 28. 56 over 2 is 28. So if we found out that A times B equals to 28. But we already found out that the area of the big triangle CN equals to A times B. And again, we only found out that the area of the big triangle CN equals to A times B. We can write here that the area of the CN equals to A times B, but we just right now found out that AB equals to 28, so we can write here that AB equals to 28, and from this equation, the area of the big triangle CN equals to AB equals to 28, we have that the area of the big triangle CN equals to 28 square units in size. Those two sides of the equation are equal to each other. So the area of the big triangle CN equals to 28 square units in size. We already found out that the area of the green triangle CO equals to the area of the big triangle CEN over 2. Then again, we found out that the area of the green triangle COE equals to the area of the big triangle CEN over 2. The area of the green triangle CO equals to the area of the big triangle CN over 2. but the area of the big triangle CN is 28, so we can substitute the area of the triangle CEN by 28 over 2. 28 over 2 is 14. Those two sides of the equation are equal to each other. That is to say that we found out that the area of the great triangle COE equals to 14 square units in its size. In the next step, we calculated the area of this great triangle COE according to the rule that the area of any triangle equals to the base of the triangle times the height of the base over 2. And again, the area of the great triangle COE equals to the base of the triangle times the height to the base over 2. We already found out that the area of the triangle COE equals to 14 square units in its size. Now we calculated the area of the great triangle COE according to the rule that says that the area of any triangle equals to the base of the triangle times the height over to the base over 2. So we choose the base of this great triangle COE as OE. The base is OE times the height to the base. The height to the extended base is EA. The height must create 90 degrees with the extended base. The extended base is EA, and CD creates 90 degrees with the extended base EA. Therefore, CD is the height of the base of this triangle COE. So in total, we found out that the area of the triangle COE equals to the base OE times the height of the base, that is CD over 2. OE equals to 5 units in its length according to what is given as a question. CD equals to X, according to what is given as a question. X is the line segment that we are looking for. So we substituted OE by 5 and CD by X. So in total we found out that the area of the great triangle COE equals to 5x over 2. But we already found out that the area of the great triangle COE equals to 14. So we can write that the area of the great triangle COE equals to 14. And for this equation, 14 equals to the area of the great triangle COE equals to 5x over 2. We'll derive that 14 equals to 5x over 2. 14 equals to 5x over 2. Here we multiplied this equation by 2 and finally found out that 14 times 2 is 28 equals to 5x. Here we divided this equation by 5 and finally found out that x equals to 28 over 5 units in its length. 28 over 5 is 5.6 units. So in total we found out that the left line set CD is equal to x is equal to either 28 over 5 units in its length, or in terms of numbers, the left of line set CD is equal to x is equal to 5.6 units in its length. Okay, thank you very much.